Alright, so we've been going over all this, the kinematics of 3D motion. We've been dealing with the rotations and stuff, and the whole point was to get this, the point of those discussions was kind of to get to this point where we can describe in general the 3D dynamics of a rigid body. Alright, and so we've kind of, when we're dealing with particle dynamics, we can apply those almost directly when we're dealing with particles when it comes to the linear momentum equation. All right. This is the exact same equation as long as we sort of modify it that the particle that we're speaking is the center of mass of the object. Okay, and so we've already kind of beaten these to death. What we haven't dealt with is the rotational components. So moments about G. So this body, this arbitrary body here, is acted on with the if that force, you remember, moment is just we'll call it the moment is this cross product of the position vector and the force. So if the force is acting in such a way that it passes through G, like this is slightly offset, so maybe I could have made it a little bit more obvious, but this is slightly offset, so it's going to result in a rotation of the body in that direction. Right, the whole body is going to start to rotate because the force is being offset. So if the force were, say, pointing this direction and offset from the center of mass, it'll cause a rotation about the center of mass. All right. So the moments about G are just going to be the sum of all the individual forces and the moment arm that's created by the fact that the force isn't passing directly through G. Okay, so the moments about G are equal to the time derivative of the angular momentum about G. And we've revisited this when we talked about angular momentum to begin with. We were talking about systems of particles, and this is the same equation. Okay. Now, because we're dealing with a rigid body, we defined what this relationship about the inertia tensor. So in general, if we're going to be dealing in terms of the inertial frame, which is for these equations to be valid, so these are valid in inertial frames. So it's valid in the XYZ frame, okay? However, when we take this derivative, we have to account for the fact that the inertia tensor changes as a function of the orientation of the body. Well, the tensor itself doesn't change, relative to the body, but the individual components of the tensor change in reference to the XYZ frame, the capital XYZ frame, the inertial frame. Okay, so this time derivative is non-zero if we try to just do the analysis completely within the inertial frame. Okay, so we would like, so the problem, so if analyzed with respect to the inertial frame, the XYZ frame, capital, this is not equal 0. Okay. So we could simplify the problem greatly if we analyze it in terms of the rotating frame. Pardon my spelling, I'm terrible at it. I guess that's right. Because I was right the first time. So we would like to analyze the problem in the rotating, I say maybe in a rotating frame. I don't have I've talked about this yet. In a rotating frame fixed to the principal axes so we were talking body, and remember in the principal axes I'll signify that with this lowercase xyz. It's particularly simple, the inertia tensor is. By definition, it's diagonal. That's what makes these axes the principal axes. And therefore, and it's also constant. So all right. But to do that, we have to, but like I said, these equations are valid in inertial frames only. So we have to translate all of our vector components or all of our vector quantities into the associated, the inertial frame. All right. So we're going to start with so this is momentum in terms of the rotating frame, and we're after its derivative in the inertial frame, which is what we need. but remember, take this derivative, and just for completeness, I'm going to go ahead and include product rule, right? So derivative times the second plus the first times the derivative of the second. But the reason we cast this into the XYZ frame was so that this derivative wind up being 0. And so this is just equal. And remember, this is even in this simple form here, so we get like sort of a additional simplification. And so this just comes out to be okay, so that's this term. Remember what omega is, capital Omega. Capital Omega is the angular velocity of the reference frame. In this case, we've chosen the reference with the body, and the body is rotating at the velocity of lowercase omega. Okay, so use this definition here. So we're getting closer. And everything on this right hand side is evaluated in terms of the rotating frame. Now, it's kind of hand wavy at first, but just realize that this is a vector, and because frame and the rotating frame are at this instant coincident with one another, or aligned with one another, I guess. Not necessarily coincident, but aligned with one another. So the X and the X and the Y and the Y and the Z and the Z are aligned. It doesn't matter which reference frame. We're not talking about a derivative here. We're just talking about the vector itself. So the components are the same. It doesn't matter which vector we're dealing with. So now we got to carry out this cross product. So in general, remember the cross product. So if we have two vectors, A cross B, we take that cross product using this sort of kind of a shortcut, or this is like a little way of helping us remember the okay. So in this, we have A would be omega, and B would be this product of the inertial tensor. So first, let's compute what that is. And we've kind of already done that. It's just going to look just like this without dots. We'll take that to be equal to B, and then all right. And so now, so the X, so it's AYBZ. So we need let's see. Simplify that. putting this all together. And remember to the moments. So we get three. These are component. Everything in this equation is a number. There are no vectors in this. These are just the components, right? Solve into a computer in order to solve. All right. Now, remember, if we wanted to solve these are differential equations, and they're difficult differential equations, um, coupled, right? So here's a equation in terms of omega x, and it y and omega z. So they're coupled, three coupled differential equations. In general, we solve these on a computer. However, we're going to make some simplifications. Most of the problems, so we went through this and we've been talking about the general motion of a 3D object. Okay. However, we're going to take a step back. I think it's important that you understand where this stuff comes from, and then it's not as simple as maybe what you learned in physics 2. Like we weren't introduced to at least I wasn't introduced into the inertial tensor or anything like that in introductory physics. However, it's important and it has some consequences especially when we're talking about 3D. What's done. So now we're going to take a step back and apply some simplifications, and for the most part, we're going to solve these equations in terms of planar motion for the majority of the rest of the semester. So we're going to take a step back. I'm going to show you where these simplifications come in, and then we're going to start solving problems that are a little bit, well, quite a bit simpler than these general solutions. By the way, these equations, they have a name. They're the Euler. Euler. But these are with rigid body dynamics.